So now let's look at L1 theta A. Let me just consider a to power theta minus 1 whole square. So I'm estimating only theta, not theta to power m. Theta to power m, you can repeat the same thing. So what is the Bayes estimator in this case we have seen? This is expected value of s given x of 1 upon s. So when you put 1 upon s over here, so that means 1 by theta would come, it would come summation xi plus alpha minus 1 minus 1. So it would become here gamma xi plus alpha minus 1, and so it would become n plus 1 by nu to power summation xi plus alpha sorry, only in this much, because there alpha minus 1 would come and that would get cancelled, and this divided by summation xi plus alpha divided by denominator would be 1 upon s square. So when you take x to s square, this integral 1 upon theta square, that will make it here summation xi alpha minus 2. And if that is the case, then here you get n plus 1 by nu square divided by summation xi plus alpha whole square, right? This usual gamma integral. And what does that give? That gives you summation xi plus alpha divided by n plus 1 by nu. So again, the same estimator, right? Summation xi plus alpha n plus 1 by nu. So in both the loss functions, you get the same estimator. Now note that over here, when very small special thing is happening, that here prior distribution is such that the posterior prior distribution was gamma, and the posterior distribution is also belonging to the gamma family. So whenever such a thing is happening, that means the prior distribution and posterior distribution belong to the same family of distributions. For example, in this case, gamma family of distributions. We call such a prior as a conjugate prior. So let me give the definition of a conjugate prior. So one thing you should, which you noted in the above example is, in the above example, so let me write down example as EG, the prior distribution and the posterior distribution belong to the same family. If such a thing happens, we call such a prior distribution as the conjugate prior. So let me write down. If the prior distribution is such that if the prior distribution is such that the posterior and the prior distribution belong to the same family, now that same family, for example, could be gamma family, normal family, because gamma is a family of distribution. Normal is also a family of distributions. Beta is a family of distributions. If such a thing happens, we call such a prior distribution to be the conjugate prior distribution. Then such a prior is called conjugate prior. Now, example of conjugate priors is they are easy to handle because normally prior distribution you would use which are tractable. So posterior distribution then also becomes tractable, and deriving Bayes estimators and its properties becomes easier. Of course, the drawback is once you are restricting only to the conjugate prior, you're restricting your choices of prior distribution. So the whole analysis which you get may not be that robust because you have restricted your class of prior distributions. So for example, here I restricted my class of prior distributions to be the gamma, although gamma itself is a very rich class of prior distributions because there are two parameters. I can play around with those parameters, but those parameters, all the cases, most of the cases, your distribution would be unimodal, skewed, and depending on alpha and nu, if I have that kind of a prior information that my theta from the past experience can be modeled through a unimodal PDF with the skewness present over there, such a choice is okay. But still there is some compromise. That means you're only restricting to the gamma, and gamma has limited properties. So that's one slight disadvantage, but a major advantage is that restricting to the prior, which is conjugate, makes studying all those properties much easier. Okay, so this was about conjugate prior. Let me move further. Now sometimes, you see here I have quantified everything in terms of a proper probability distribution. Now sometimes your prior distribution may not be a proper probability distribution. That means it may not integrate out to 1. So a prior pi is called improper if it is not a probability measure. That is integral over theta d pi theta is not equal to 1. Now note that as long as it was a finite quantity, I could have made it a finite measure. I could have made it a probability measure because I divide that, I absorb that constant where it integrates out to in the PDF, and then the total PDF area becomes 1, and it becomes a probability distribution. So in fact, normally it is the case when theta di theta is infinity, because finite measure can always be converted into a probability measure by dividing that by division through that normalizing constant. So if integral over theta d pi theta was c, I could have taken d pi theta upon c as the PDF. So normally when I say that a prior is not proper, it means total integral is infinity, right? Now the question is why you need improper prior. Purpose of improper The purpose is as follows. Sometimes it is preferable when you don't have a prior information available to you, which is like a classical sense. So prior information you might have available, but the prior information is such that it does not favor one point over the other point. So it doesn't favor one parametric point over the other parametric point. So like a uniform prior. So it gives the same weight to all the priors, all the points in the parametric space, which you also call as a non-informative prior. So non-informative prior. So let us look at, suppose you have a x, which is normal theta A, normal theta 1. And what I know is theta belongs to A to B, the closed interval A to B. A prior, a uniform AB prior on can be considered as non-informative prior. And non-informative in the sense that it says, in certain sense, I do not give more weightage to one set of points. It is uniformly distributed in A to B. So same set of weightage is given to the neighborhoods of all the points. So that was okay if theta was between A to B. Now suppose theta is between whole to R. And what is the property of a uniform distribution? Uniform distribution has a characterization that the probability of any interval, subinterval of AB is proportional to the length of the interval. Nothing that it doesn't depend on where that interval is located. It only depends on the length of the interval. So that means if I take any subinterval of A to B, it only depends on the length of the interval. The probability which is assigned to it only depends on the length of the interval. It does not depend on where it is located. For example, when I am talking about uniform 0, 1, if I consider the interval 0 to 1 by 4 or 3 by 4 to 1, the length is same, but they are located at different extremes. But here the weight given to 0 to 1 by 4 and 3 by 4 to 1 is the same, which is 1 by 4, which is equivalent to the length of the interval. So uniform distribution has a property. That means when I'm talking about non-informative prior, what it says is the probability assigned to any interval is only depending on the length of the interval. It does not depend on where it is located. It was very easy when the interval A to B was finite. Now suppose I know that theta belongs to R. What would be the kind of a non-informative prior? Non-informative prior means the weight which I give to an interval only depends on the length of the interval. It does not depend on where it is located. And you know such a measure is called the Lebesgue measure, because Lebesgue measure is nothing but only the length of the interval. So Lebesgue measure gives same weight to intervals having the same length. It does not depend where that interval is located. So, and what is the Lebesgue measure? That means my pi theta or pi of B is nothing but integral over B d pi theta. So what would be pi of R? And this is a Lebesgue measure. And basically this is nothing but d theta, right? Lebesgue measure you write down as d theta only. You integrate. So this is a Lebesgue integral basically. Integral of B. So pi of r is integral over whole of r of d of theta, which is nothing but infinite. So it made sense to have sometimes prior, which are not proper, but they are some kind of approximations of proper priors. Because as a goes to minus infinity and b goes to plus infinity, uniform AB becomes nothing but the Lebesgue measure, because it only depends, the weight given to any interval depends only on the length of the interval, not where it is located. So that way, sometimes making studying improper prior makes sense. So I can talk about now the generalized Bayes estimator. A generalized Bayes estimator would be one which minimizes the posterior expected loss with respect to this prior. Now here actually if you look at posterior, it doesn't make sense because pi is not a probability distribution. But I can look at what was the quantity I was trying to minimize. Posterior distribution was a normalizing constant which comes outside the integral. Then L theta a, inside the integral L theta a, f theta x, and the prior fs theta. So I can think of minimizing this, except that now fs theta may not be a proper probability distribution. So I am now in a position to define what do you mean by a generalized Bayes estimator. So suppose pi is an improper prior. Improper prior, that means its total integral is infinity rather than 1, because for proper prior, total integral has to be 1. Suppose pi is an improper prior, so that means integral over theta d pi theta is nothing but infinity. An estimator delta star x, which is let me call as ax, is said to be generalized Bayes if for every x in the sample space, what has happened? L, so posterior, so that means integral over theta, L theta ax of f theta x. It is like a posterior loss I am talking about. In the posterior loss, the posterior distribution was coming, and posterior distribution is not proportional to the f theta x into the PDF of theta d theta. Is same as infimum over a in the xn space of theta L theta a f theta x. So this basically what you say is a generalized Bayes estimator is nothing but a Bayes estimator against an improper prior. Because if fs was proper, then this was nothing but a Bayes estimator, which minimizes the posterior expected loss. So I can also talk about the posterior expected loss when the prior distribution fs theta is not a proper. And I define that posterior expected loss like this. So that leads to the concept of generalized Bayes estimator. So in the Bayesian theory or Bayesian analysis, improper distributions or improper prior distributions play a very important role. as we'll see later on. We realize that in certain sense, Bayes estimators are very restrictive. Sometimes extending this class of Bayes estimators makes sense. And normally it so turns out that these generalized Bayes estimators turn out to be the closure of all the Bayes estimators. Closure in the sense, that means in certain limiting sense, these generalized Bayes estimators are nothing but limiting forms of certain Bayes estimators. So as I said, for example, if you consider that prior, gamma prior, and I have said that if you alpha going to 0, nu going to infinity, I go back to some classical situation where I don't have any prior information. So here I am talking about a prior distribution in terms of in certain limiting sense, because as alpha goes to 0 and nu goes to infinity with certain rates, you may get a PDF which is not a proper PDF, and which may be an improper PDF. But studying such a PDF, which is a limiting PDF, makes sense, or in other words, studying Bayes estimators in limiting form makes sense, or limiting Bayes estimators, their study is important. So it is in that context, generalized Bayes estimators are important. So we'll continue from here in the next lecture. That's all for today. Thank you very much.